who escape attack. And this is a proportion, F. I've actually got my own of these, so let me use that. So this is F, N of T, P of T. So this is, remember, this is a proportion that escape attack. It's the escape function, and it's a proportion. So not all of them grow, only the proportion that escape attack grow. So this will say, you know, for every adult in this generation, I would get so many new individuals in the next generation, and lambda would be the basic growth rate. So this reflects the rate at which these particular hosts lay eggs and their young develop and probability of surviving and so on. And you have this replication rate of lambda, but this rate is reduced by the proportion that are attacked. Now what about the parasitoid population, P at T plus 1? So now it's the proportion that do not escape. This proportion that do not escape. So if F is the proportion that escapes, then 1 minus F is the proportion that don't escape. And then the number that don't escape would be N of T times that proportion. Now each one of these can develop into a parasitoid in the next generation. But because there's some mortality rate, we'll put a constant C here. So C says that for every one that is attacked, only a proportion C of them will produce a new parasitoid. And the reason why we have this not equal to 1 is that there are many things that can happen. A bird can come up and eat this larvae, and so the parasitoid that's developing inside there gets eaten as well. Or maybe there were 3 parasitoids laid in here, and they fought with each other and nobody made it. There are all kinds of different reasons why you need a constant in there that's not equal to 1. Okay. So now what we can do is we can say, okay, we're going to really simplify this. And instead of saying that this is a very general function, what is important is not the density of n and the density of p, but the rate at which p encounters n. So I'm going to replace this function over here with the encounter rate. So I don't really care how many parasitoids and how many hosts I have. All I care about is the proportion of times a parasitoid encounters a host. Now, there are 2 models for the encounter rate. The first model says that every parasitoid P has a certain number of eggs, let's say beta eggs. So Thompson's model is the egg-limited model. In the egg-limited model, what we say is that if we have P parasitoids, then we have beta times P eggs. And if they're beta times P eggs, then they're beta times P upon N eggs per host. So it's like we've got a bunch of eggs out there, and this would be the number of balls, and this would be the number of boxes. And so this would be our parameter, and this is called the mean encounter rate. But if we have a Poisson distribution, this would just be this would be the mean in the Poisson distribution. This is the mean number of balls per box, so to speak, so the mean number of eggs per host that are available. And in the Poisson model, we know that the proportion of individuals that are not attacked is just given by, therefore, in the Poisson model, the proportion not attacked F is e to the minus beta P upon N. Because if we go to the Poisson model, we'll see that the number of hosts, or the number of boxes that remain empty, is just given by e to the minus the Poisson rate. And this is the Poisson rate. Okay? Everybody understand that? So if we were to build out this model, we would say, under the Poisson, we would say this is equal to lambda nt e to the minus beta pt over nt. And this is equal to c times nt, 1 minus e to the minus beta pt upon nt. So this is just a model in 2 variables, n and p, and we've derived those expressions. So you could code this up in NOVA. Does everybody think they could code this model up in NOVA? What you'd have to do is you'd have to decide what is the value for lambda, what is the value for c, what is the value for beta, and then you have the model that you just build in NOVA. So this is a 2-dimensional model. We've been building 1-dimensional models, but you'll see that it's very easy to build 2-dimensional models. And all you do in building a 2-dimensional model in NOVA is you have 2 stocks, n and p, and then you build out 2 right-hand sides, and you have your parameters c, beta, and what was the other parameter that I called it? C, beta, and lambda. Okay? And so, if you want to, you can make your function f over here. And in order to make your function f, you just need beta, p, and n. And then you can feed f into here, and you can feed c into here, and you can feed n back into here, and you can feed p into here. And you can, in fact, you don't need c in this one, you need lambda. Let's call this lambda. And c goes into this equation, and f goes into that equation. So that's how you build it. And then you just open this up and you put your equation in. Yeah? Oh, no, f is just, so the same way that you make a lambda or a beta or a c, so you make the f. Let me just quickly show you how to do this. Okay, so what we need to do is to have a stock that we call n, and a stock that we'll call P. And remember, we're going to make these discrete, so I'll start with n equal to 1,000, and let's just make it discrete here. So this is a sequence, okay? And because it can't go non-negative, you can put that in just to make sure, but you shouldn't have to do that. And P, let's start off with 5, okay? And then we can open this up, and we can also make it a sequence, and we can also make it non-negative. Now, when you run these, you are going to get non-integer values. So you can think of these as averages per unit area instead of actual numbers. Then you're going to have your right-hand side here. So you're going to have new n and new p, okay? And then what did I say? You need a lambda, an f, and a c. So we take this out, and we get lambda, a beta, and a c. Beta, okay? And c, okay? And then you can make a function f, like that, f. Okay, and to make this function f, you need beta. That's going the wrong way. And you need n. And you need, okay. So now, in order to make f, so f is equal to, now I forgot how to do exponential in JavaScript. So what do? I'll go here and say, okay, I think it's math.exp. Math.exp. Huh? Oh. What are you saying it is? Yeah, but okay, then I've got to put exp into it. Okay, so I want to find what the exponential function is. But that may exponential function in JavaScript. It's probably also there in the... So this is just the function e. I'm not looking for exponent. Huh? Just math.e. Okay. So let's try that. Yeah, I hate JavaScript for this reason. Math.pow, and we're taking, so the base is going to be math.e. Is that right, Eric? Capital E. And then the exponent is going to be equal to beta times p upon n, and it's going to be minus. So we're going to be minus beta times p divided by n. Okay, so I think that should work, I hope. Okay, so now in order to create this equation over here, you've got your f, and you've got your lambda, and you've got your n. And so we need f and lambda and n, and we just need to multiply them. And in order to create this equation over here, you need your f and your n and your c. So f and n and c. Okay, and so now you build these functions in here. So that's just going to be equal to lambda times n times f. And then I'm not going to finish building this. But anyway, that's the way you do it, okay? Everybody understand that? Okay, so it should be straightforward for you to build it. But now this epsilon is the encounter rate under egg limited. If we're under search limited, then you get epsilon is not equal to beta p upon n, but you assume that there's some searching rate, and that the encounter rate of a host depends on the number of parasitoids and how actively they search. So the bigger A is, the more rapidly they search an area. So if from the host point of view, how many parasitoids are going to see it? Well, it depends on the number of parasitoids flying around and how rapidly they fly around. So it's just proportional to A times P. So here's a model where epsilon is equal to A times P. Now here's a model where you can combine the two. So you say epsilon is equal to A times P as long as the parasitoid has eggs. And so this expression says that it's proportional to P as long as the parasitoid has eggs. And when the parasitoid runs out of eggs, then the function depends now on the number of eggs. So you get these two functions. You get the being search limited if there aren't enough parasitoids, but if there are a lot of parasitoids and there are a lot of hosts, then it depends on the number of eggs out there. So you can express this function in two ways, and you can combine it. This is something that you will explore in your homework. So basically, the Poisson model says that if the encounter rate, if it's a Poisson process, then the number of hosts that escape is e to the minus encounter rate. If it's a negative binomial, then it's 1 plus the encounter rate over k to the power minus k, where k is this binomial parameter. It's an aggregation parameter. And so for different values of k, you'll get different levels of aggregation. But if you look at the limit as k tends to infinity of this expression, you'll see, if you remember your calculus, that this expression in the limit just gives you e to the minus epsilon. So you'll find this limit in calculus, and it just gives you the base e. And so this is all the machinery you need to set up the model. So here you would set up, instead of the egg-limited model, which we set up over here, you can replace this with the term AP, in which case it's the search-limited model. So you can build a search-limited model. You can find the equilibrium of the search-limited model. It's quite easy to solve for this. The equilibrium of the search-limited model occurs if n is equal to f np and p equals lambda n. I'm just writing it for the general case, and you can put in the appropriate n functional forms. 1 minus f n p. So by saying n is equal to n on this side, n of t plus 1 is equal to n of t equals n, p of t equals n, p of t plus 1 equals p. So if the p's are not changing with time and the n's are not changing with time, then you just get two equations and two unknowns, which you solve, which is what we've done here for the search-limited model. Okay, so basically you can play around with these models using NOVA. And that's what the next homework assignment is about. Any questions?